Hi everyone, here we're going to continue with the idea of torque, but now we're going to add the concept of static equilibrium. So here looking at this picture, you have a ruler that's pivoted from this support here, and you have a hanging mass on the left and a hanging mass on the right. And now the ruler is tilted towards the left. And so the pivot is at the center, and this ruler is pivoted towards the left because the hanging mass on the left here, the purple cylinder, that one is exerting a torque that's making the ruler rotate counterclockwise. So here, this system is not balanced; it's tilted, and we can even now move this box here, this bottle, to the other side. And there, if you notice, in general, in this case here, now it's tilted in the opposite direction. It's tilted in the counterclockwise direction, and this is because this bottle is exerting a torque that's making this ruler tilt in the clockwise direction. So both of these masses, the purple cylinder and the water bottle, are exerting a torque, and in general, the system is going to be in balance. It'll either tilt counterclockwise or clockwise. So to balance the system, what we want is to make those torques cancel each other out. The counterclockwise torque, you want to make it cancel with the clockwise torque. So there's going to be a special point where if you put where you place the water bottle, so that the torque from the counterclockwise torque from the cylinder is going to equal the clockwise torque from the cylinder. So effectively, there's going to be zero torque on a system, and the system is not gonna rotate. So that's the first equation when we look at a static equilibrium, that you don't want the system to rotate, so the net torque is going to be equal to zero. Let's look at this setup here. So here, what you're looking at, so you have a wall with a pivot on the left here, and you have a beam, and the beam is connected to a cable. Even though this says 85, let's just assume that it's 90 degrees, because this will be closer to the experiment. And then you have a mass here. So the things that we can adjust the mass of the block, and we can also adjust the position of the block. So that's the position D here. So now let's look at the forces that are present in this case. So if you show the free body diagram, we're going to ignore the forces on the pivot. So let's look at the other forces that are present. I'm going to move the mass. So here, first, the beam has a mass, and its mass is concentrated at its center of mass. So that's going to be this one here, the mass of the beam. Next, the beam is there's a cable connecting the other end of the beam, the right end of the beam, so that is going to exert a tension force. And so we can see that tension force there. And the other thing is now there's going to be another mass, the one that we can move. So that one is also going to exert a force as well. So each of these, so the pivot point is on the left, so each of these other forces, the weight of the box, the weight of the beam, and this tension force, they're all going to exert a torque. They're all exerting forces, so and a torque. So let's break it up into individual components. So first, just considering the forces, according to Newton's second law, let me just simplify this diagram some here. So if you look at this is a better picture, because here the tension is a vertical force. So in this case, in a vertical direction, there are three forces, but in general, this beam is going to stay horizontal. So the only way that is possible for this beam to stay horizontal and not move vertically or fall up or down is that these forces have to balance each other. So one of the first condition for static equilibrium is that the total forces acting on the system are going to be zero. So those are just the forces, but now each of these, now we're going to consider this in terms of the torque. So now the pivot point is on the left here, and each of these forces are at some distance away from the pivot point. So that means that each of these forces are going to exert a torque. But again, like we saw in this picture here, the beam in general is not going to rotate up or down. So because of that, the sum of all these torques also have to equal to zero. And those are the two conditions for static equilibrium. The first thing is that the net force on the system has to equal zero. And the other part is that the net torque from these objects away from the pivot has to also equal zero. In this case here, the tension exerts a torque that makes this beam rotate in the counterclockwise direction, and these other two torques, the weight of the beam and the mass of the block, they tend to exert torques to make the beam rotate in the clockwise direction. But they effectively cancel out so that there's no torque on the system.